Hello everybody, welcome back. Let's continue our look at bonding. And today we are going to be focusing on molecules, covalent bonding and Lewis structures. Please start by opening up your IB data booklet so that you can see a periodic table in front of you. Get a pen or pencil and paper so you can have a go later at drawing some Lewis structures yourself. Hit pause now while you do that. Okay, welcome back. Now, I'd like you to please make a note of the definitions I've got at the bottom of the page here for molecules, for covalent bonding and for Lewis structures. Molecules are groups of atoms held together by covalent bonds. And what do we mean by a covalent bond? Well, a single covalent bond is an attraction between the nuclei of adjacent or neighbouring atoms and a shared pair of electrons. Now, why does that happen? Remember, nuclei are positive. They're positive because they contain lots of protons, and electrons, of course, are negative. So we get an electrostatic attraction between those opposite charges, and that is what we mean by a covalent bond. Lewis structures are diagrams simply which show the valence electrons. Valence means outer shell, remember, outer shell electrons only, of atoms, ions or molecules, and we can represent them in a number of ways: as dots, as crosses. We can use both dots and crosses, or we can use a straight line to represent a pair of electrons. So pairs of electrons can be pairs of dots and crosses, or lines. Those all three represent pairs of electrons. Now pause and make a note of those definitions. Okay, welcome back again. Next, I'd like you please to make a note of the table I've got here. Just make a note of that table, thanks. Hit pause. Okay, welcome back. Now, you've got your periodic table in front of you, I'm hoping. And let's figure out how to complete this table I've got. Before we do so, let's remember that the driving force behind bonding is this tendency of atoms to achieve a full outer shell of electrons, a full valence shell. Achieve a full outer shell of electrons. That's the driving force behind bonding. Now, for all elements except for hydrogen, that means getting 8 electrons in the outer shell. For hydrogen, it's just 2 electrons, but for everything else, it's 8 electrons, and that's why we often refer to this as gaining a full octet. And so the rule we're going to be using today is the octet rule. Now, group 4 atoms, if you remember, group 4 atoms will have 4 electrons in their outer shell. So in order for them to get a full octet, they need an extra 4 electrons. That can happen by sharing those electrons. So if I have a group 4 atom, if it makes 4 covalent bonds, it's going to have a full octet. Group 5 atoms have 5 electrons in their outer shell, so by sharing another 3 electrons, or forming 3 covalent bonds, they'll get a full octet. Likewise for group 6, they need to form 2 covalent bonds to get a full octet. Group 7, 1 electron pair or 1 covalent bond needs to be shared, and hydrogen, which has just 1 electron in its outer shell, can also form just one covalent bond. So with those rules under our belt, we can now have a go at working out some Lewis structures. We start with the simplest element of all, hydrogen. Hydrogen is a diatomic. Thank you, Mr. Brinkelhoff. Hydrogen is diatomic, so if it's going to form a covalent bond with another atom, we can draw that by its side using the chemical symbols capital H. Now hydrogen can only form one covalent bond. Let's just start by showing that one covalent bond there, and remembering that that covalent bond represents 2 electrons. So we could also illustrate that with a dot and a cross, or as 2 dots. Any of the 3 representations are perfectly acceptable for the Lewis structure for hydrogen. Moving on to fluorine. Fluorine is in group 7. It's here. It's got 7 electrons in its outer shell, and so it can form just one covalent bond in order to get a full outer shell or a full octet. And if it's F2, again, Brinkelhoff, thank you, we can put the next fluorine next to it. We know it can only form one covalent bond, so there's the covalent bond. But, and here's the important point, often forgotten by students, is that the Lewis structure shows all of the valence electrons. At the moment we've just shown the bond. Let's fill the others in. The covalent bond, remember, represents 2 electrons. So we've got 2, 4, 6, 8 electrons around that fluorine, and 2, 4, 6, 8 electrons around that fluorine. There was no reason why I changed to red ink, so I'll just draw it out again. For fluorine, we could do this. If you're using a ballpoint pen, it's very wise to make sure you leave a dot there. And another possibility for representing that is as follows. Some of you might prefer to use those straight lines, which are quite acceptable as electron pairs. Any of those 3 representations works just fine. Moving on, methane, CH4. Carbon is in group 4. So it's got 4 electrons in its outer shell, and it can form 4 covalent bonds. There it is. And hydrogen, remember, can only form 1 covalent bond. So if we show the hydrogen atoms here, the hydrogen atoms cannot be bonded to each other because they have to be bonded to carbon, otherwise carbon couldn't form 4 covalent bonds. And if I put in the covalent bonds, 1, 2, 3, 4, we've shown the 4 covalent bonds for carbon, and each hydrogen has got 1 covalent bond. And if we just count, carbon now has 2, 4, 6, 8 electrons. It's obeyed the octet rule. And each hydrogen has got 2 electrons. 2, 2, 2. Hydrogen only needs 2 to have a full outer shell. And if we like, we could also represent that as so, showing the full octet for carbon and hydrogen. Next, we have ammonia. Nitrogen and 3 hydrogens. Nitrogen is in group 5 over here. So it's got 5 electrons in its outer shell. It can form 3 covalent bonds. Let's put them in straight away. 1, 2, 3. They must be going to hydrogen atoms. Remember, hydrogen can only have 1 covalent bond, so hydrogen cannot go between 2 atoms. It cannot be bonded to 2 atoms at any point. Nitrogen now, if we look, has just got 2, 4, 6 electrons in its outer shell. Now please remember, the octet rule states that all the atoms we're using in this model are obeying the octet rule. So nitrogen is missing 2 electrons. So if we've got 2, 4, 6 electrons there, we can add in another pair of electrons here to give us 8. And that pair of electrons, which is non-bonded, we can call either a lone pair of electrons or just a non-bonding pair of electrons. And again, if we want to write the ammonia molecule out again, we could do it like so. With the dots there. Or of course, using just dots, or a combination of dots and crosses. Either is acceptable, just making sure that nitrogen's got its full 8 electron shell. Moving on, water. H2O. If you look in your periodic table, you're going to find that oxygen is in group 6 with 6 electrons in its outer shell. So it needs to form 2 covalent bonds. There are 2 hydrogen atoms. Remember, hydrogen can only be bonded to one other atom. So that means that the 2 covalent bonds from oxygen have to go there. That gives me 4 electrons around oxygen. Again, everything's obeying the octet rule, so let's fill in the others. 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons around oxygen. It's obeying the octet rule. So water can be shown like so. Or, if you choose, it could be like so, or like so. Anything's acceptable here, as long as we're showing the electrons as dots, crosses, or lines, though a line represents just a pair of electrons. Carbon dioxide. Carbon, remember, is in group 4. Oxygen is in group 6. Carbon needs to form 4 covalent bonds, and oxygen 2 covalent bonds. Well, for oxygen to form its 2 covalent bonds, it could do a bond between carbon and oxygen. There's those bonds, and here between that oxygen. So carbon has got 2, 4, 6, 8 electrons in its outer shell. It's obeying the octet rule. Oxygen, though, has just got 2, 4 here. So let's put those other 4. 5, 6, 7, 8. 5, 6, 7, 8. So oxygen has got 2, 4, 6, 8 electrons there. 2, 4, 6, 8 electrons there. So for carbon dioxide, we can show the Lewis structure like so. Or, if you choose, with the lines, we could do it like that. Oxygen, diatomic again. Thank you, Mr. Brinkelhoff. Oxygen only can form 2 covalent bonds because it's already got 6 electrons in its outer shell. If there's only 2 oxygens, they must be bonded together, and there are the 2 bonds. A double covalent bond, stronger than a single covalent bond and shorter. That amounts to 2, 4 electrons. 5, 6, 7, 8. 2, 4, 5, 6, 7, 8. So we can represent that again like so, or of course like so. Nitrogen, thank you, Mr. Brinkelhoff. Diatomic again. Nitrogen is in group 5. There's 5 electrons in its outer shell, so it needs 3, which can be obtained by sharing 3 electrons with each other atom. So there's the triple bond, the 3 covalent bonds. That gives us 2, 4, 6 electrons. 7, 8 electrons, 8 electrons. So nitrogen now, each nitrogen has got 8 electrons in its outer shell. Here's another one. This compound, remember, is called ethene. Carbon forms 4 covalent bonds, hydrogen just 1 covalent bond. Hydrogen then has to only be bonded to one other atom. And the only way that can work is by having the covalent bonds between hydrogen and the carbon atoms, like so. That gives just 2 covalent bonds to each carbon, and the other 2 can be a double bond. So if we count up, carbon has got 2, 4, 6, 8 here, and 2, 4, 6, 8 here. So we've correctly deduced the Lewis electron dot structure for the organic compound ethene. Now, I suggest you think about that, have a look through those, and then you can work your way through this exercise, drawing out the Lewis electron dot structures for the molecules shown. And of course, in each case, you're going to assume that they're all molecules. Thank you. Good night.